Hello again, everyone. This is Cognitive Science 501, Algorithmic Structures in Cognition, and at the Middle East Technical University. And this is the final lecture, sort of bringing everything together lecture. So I'll start with one clarification from week 13. So if you remember, at the end of week 13, I said, well, probability of a joint probability of tree and sentence can be described as a product of probabilities of rule use and given the sentence. So given the right hand side, given the sentence, what can I do about rule use is the idea. This is clearly a bottom-up way of constructing forms and meanings, because I take the right-hand side as given, that is recognized. I take the sentence, and from this I try to figure out which rule to reduce by. And if you keep doing that, you're going to reach the star symbol, and that will be the root of the tree. So this is what I meant, but I think I wrote something else. I clarified that in the comment section of the video. But in case you missed it, this is what I had in mind. So we're working on that, and I'm going to work our way up to integrating everything: syntax, semantics, computation, and uncertainty. 4 things. By looking at a more deterministic grammar in the first place, like the grammar of arithmetic that I showed you. And I asked a question about that in the last quiz, so I'm going to the quiz before that, I think week 12 quiz. So I'm going to talk about that, and then I'm going to move into the more non-deterministic grammar, where, like, I saw the diameter telescope gives you several different interpretations. That was the last quiz, and where we wanted to write, given a tree, the computation was deterministic, but which tree to choose was not deterministic. So I'm going to try and integrate probabilistic inference into that one by one. So let's work on the first one. So I'm trying to remember the quiz. I gave you something like this. And I said, if the meaning of this is S prime, the meaning of this is plus prime, and the meaning of that is, let's say, T prime. The meaning that you combine here is like, give me the first one, second one, third one. Then in the body, I'm going to do, this is the function, and these two are the arguments. So this is a lambda term. These are what is provided by these. I'm going to write them down. And this is, I'll take these two and interpret them according to what the function is. So at this point, you don't really know what the function is, but once you recognize the right-hand side, you're going to know what x, y, and z are, and you're going to interpret this. Okay? And then I said, well, you know, one way to do this is you take t to s to t. If this is t prime, basically what you're doing is, well, this, since it doesn't combine with anything, it just says, give me that, and I apply this to this function, and t goes to f. If you remember my rule, and f is like, let's say the meaning of this f prime. This will say lambda x val, because after all this is not combining with anything, so I'm just projecting the value. And here I said, well, it could be 3 or it could be 5. But if it's 3, then the value is 3. If it is 5, the value is 5. And since, again, you're not combining, you're just projecting things up. Okay. And the question was, build a bottom-up PDA for this, and then compute 3 plus 5. So when you do the PDA, you're going to be doing the actual computation. In other words, it's going to give you the value of 3 plus 5 as you recognize forms and meanings up to 3. Okay, so keep this grammar in mind when I write the PDA. You know the algorithm. I'll just remind you the basics of the algorithm because I think it's crucial. I mean, if you're wondering how the PDA, which just works over the form, puts the semantic form in the stack. If you recall, there are two kinds of actions that the algorithm for generating PDA does. One is rule use, which means evaluate and insert value into stack. Push item to stack. So rule use means you have a rule that projects up. When you push lexical items, symbols onto the stack, in the surface string, they don't have meanings represented with them, right? So they just have the form. So scan the item and push its semantics into stack. This is what you do. And you can do this because if you, just to give you an example, if you have that, this is where you are. I mean, this is what you have on the string. You have the number 3, and this number has the value of 3, but this is not, this part is not in the input itself. This is in your grammar, okay? So, so if you do it that way, the PDA was going to look like this. So for every rule, if you have P, nothing, and then something sitting on top of the stack in reverse, so like if this is the top of your stack, then you push. This is the rule for S written in reverse. So you're going to do, you're going to push S because the left hand side says X. This says the meaning of this is lambda X, lambda Y, lambda Z, if you remember. Y, X, Z. And because you're at this point, you have access to this, this, and that, you're going to introduce plus prime, s prime, and t prime. You're going to evaluate these with that, and that's going to be in the stack. Okay. So I don't do anything on the input. I recognize the right-hand side. I reduce it to the left-hand side. Similarly, you can do it for other rules. Let me write another one. Let's write the t rule. If you have t on top, then t's left-hand side is essentially s again, and this time its lambda form is lambda x, and to that you provide this meaning. Okay. So you're pushing these things onto the stack. In other words, you're calculating on the fly. Okay, and there are two more rules, because there's a t rule, there's an f rule, there are two f rules. One critical thing is once you have that, for instance, once you have 3 in the input, you don't do anything onto the stack. You push this into the stack. You're pushing value into the stack. But since the rule that allows to do this is because this is a terminal, and it's separated by a pre-terminal, you know that this is going to be introduced the value 3 prime or 3. Okay. So, right. So these are rule use. This is insert. The critical bit is, this is the rule use, that is, I'm combining something by applying the rule. Here, I'm saying I have something, and in my grammar, I have that with the meaning this. I'm putting that into the stack. You keep doing this. So as long as you know that it's only for constant symbols that you don't manipulate the stack and put it into the, you don't pop the stack, you push into it. But when you use a rule, you pop the stack and push this into the rule, into the stack. And in the end, if you remember the acceptance condition, it says, well, if you keep doing that, and in the end, you get something, then you go to Q with nothing left in the input, and this will be the result. Because only the accepting state is Q, recall. So I go from P to Q only if there is S sitting on top of the stack, and I move to Q and I only accept in Q. And remember the acceptance criteria: if the stack is empty, if I'm at the end of the input, I can say yes. Otherwise, I'll say no. Okay, at least no to this sequence of computation, because it might in principle be non-deterministic. Okay. So in case of PDA, you accept if there is one path from going P to Q, emptying the stack, taking care of everything in the input, and ending in a final state. If there is at least one path of computation like that, then you can say yes, and you say, well, here's the result. Okay. So if you keep that in mind, how are we going to compute 3 plus 5? Okay.